In this question, we're given a graph of NO2 in atmospheres versus time in seconds. And the first question it says, is NO2 being created or destroyed by the chemical reaction? Well, if you notice, as time goes on, there are less and less atmospheres of NO2, so NO2 is being destroyed. It's sloping down. If we're sloping up, whether it's a curve or a straight line, doesn't matter, and we're getting more NO2 through time, then it would be being created. If it was a straight flat line, it would be neither created nor destroyed. So that's probably the easiest question on here. The next question is pretty challenging. It says, if NO2 is being created or destroyed, what is the rate at which it is being created or destroyed 90 seconds after the reaction starts? So here I'm going to use just a straight edge to do this. On Alex, I'm not sure if they give you tools to be able to do this, but I'm going to do it with a straight edge. So what I want to do is go to time, 90 seconds, and then come up to the curve and mark the point. So essentially, this is the time of 90 seconds, and this is the curve. To find the instantaneous rate, I need the change in y, the change in atmospheres, over the change in x, the change in time, seconds. So it's dy over dx. But I need the tangent to the curve. I can't actually find it at this particular point. Again, I'm going to do that with a straight edge. I'm going to draw the tangent to this curve as best I can with a straight edge here, like so. So the tangent is a straight line which just touches the curve. So the blue line there is my tangent to this curve. Now I want to find delta y over delta x. Well, luckily this graph starts at 0. So delta y is 0 to 2.00. So it's 0 to 2.00, which is just 2.00 atmospheres. And then delta x is, I don't know, 210, 220, a little less than 225. So I'm going to say 223 seconds. When you take those two numbers and you divide them, you get 0.00888888 repeating. In my example, I used 225 seconds, which was 0.0089 atmospheres per second. So I should have used the 225 seconds here, measured slightly differently than the tangent line I drew on my paper. So that's why there's a slight difference. So I used 225 seconds, so it's 2 atmospheres by 225, which is 0.0089 atmospheres per second. For the last one, I need to use a separate piece of paper. I want to find the average rate at which NO2 is being created and destroyed during the first 90 seconds. So again, I want to find the point on the graph where there's 90 seconds, but this time I want to take this curve and go back over to the y-axis. Note that this is 90 seconds. The average rate is still delta y over delta x. So delta x, this is rate, is still 90 seconds. Okay, so in this case, it's the delta x is 90 seconds because I went 90 seconds. But now I need to find delta y. Well, it's 2.341 atmospheres minus, that looks like about 1.1, 1.2 atmospheres, which is 1.141, probably this is a sig fig, atmospheres divided by 90 seconds. When you do the math, you get 0.013 atmospheres per second. So in this case, we have two different examples going on. The average rate is the change in atmospheres divided by the total time, 90 seconds. So we find 90 seconds, we extrapolate back on the y-axis, and we find the difference for delta y. The instantaneous rate, here the instantaneous rate, we have to find the tangent of the curve. And then we find delta y 0 to 2, and then delta x 0 to 220, whatever, 225, and we get 2 atmospheres over 225 seconds. Note that the instantaneous rate and the average rate are not the same. So the average rate is 0.013 atmospheres per second, and the instantaneous rate is 0.0089 atmospheres per second. And that makes sense because you can see here the rate at which it's the rate at which NO2 is being consumed is decreasing as time goes on. That's why there's a slope to the curve like this.